Hi. So today we will be presenting our project on weather-aware reinforcement learning for autonomous driving. Our goal here was to see whether multimodal perception combined with continuous control RL can help an autonomous vehicle behave more safely under different weather conditions. So driving is a sequential decision-making problem, which makes reinforcement learning a natural fit, right? But RL can only perform well if the agent has a good understanding of the environment. And adverse weather creates uncertainty like fog, rain, darkness. And we wanted to test whether a multimodal scene representation improves RL-based driving policies or not. So our approach involved two-stage pipeline. So the first one was where we extracted camera images and LiDAR and pose and weather and all of those details from the Waymo dataset. And then we pre-processed all of that and fused it into a 773 dimensional, yeah, 773 dimensional vector. And then we trained a TD3 agent on this embedding with a custom reward function that penalizes risky behavior in bad weather, especially, and encourages smooth driving. So this was our perception pipeline. We used a vision transformer to encode global scene structure, which included camera and LiDAR. And we used CLIP to estimate weather categories using text-image similarity because CLIP is already pre-trained on text-image pairs. And we used LiDAR data for obstacle proximity and also to extract speed and your context from the data. So all this was already present in the TF record files inside the Waymo dataset, and we extracted all of that. And we use that as a state to our RL agent. So we picked TD3 because driving is a continuous control problem, and we need continuous acceleration and steering. And TD3 improves stability using twin critiques and delayed updates. And our reward penalizes high speed in bad weather, aggressive steering, and close obstacles while rewarding smooth and safe driving. So it's dependent on the weather as well as how roughly or like smoothly the driving is. So before RL, we trained a behavioral cloning baseline, and this model simply tries to imitate human accelerations. So it learns core strengths, but struggles with rapid changes, as you can see. So I'll just play a demo video here that we got from imitation learning as our baseline. So as you can see, the AI lacks that sudden response to change like humans do. So the behavioral cloning model shows decent correlation with human actions, meaning our feature extraction pipeline is valid, but it misses sudden accelerations, which shows why reinforcement learning is needed, and it shows us why imitation alone cannot correct errors. So TD3 training is very stable here. So the critique quickly converges and active loss plateaus, and episodic reward stays in the expected range given our penalty-heavy reward design. So this shows that the agent is consistently avoiding unsafe behaviors. And these numbers, which are MSE and MAE that we calculated, they reflect how close the TD3 outputs are to our synthetic expert actions. And given we're not performing supervised learning, these are reasonable and show that the agent produces smooth, coherent accelerations. So our biggest limitation was data. Only a single sequence in around 1,200 transitions. And we also used offline reinforcement learning, so the agent never interacted with a simulator. And the weather labels that we use came from clip similarity. As we were talking about earlier, we used cosine similarity and then one hot encoded that value using clip directly, which is approximate, but our action space also only includes acceleration and steering, and all of this can be expanded in the future work. So, for example, we could scale to more data and we could use Waymax, which would allow real sequential credit assignment. And a richer action space would also enable more complex driving because right now it's just steering and acceleration that we are predicting. And also inverse reinforcement learning could remove the need for synthetic actions, which we tried to do here. And integrating through um, most tokens from which, like actually from the paper that our design is inspired from, we couldn't use the whole pipeline. It was a lighter version of that because our design was not very complex. So the next like, future work can focus on implementing that end to end. Also, we couldn't find the code for it on, and it wasn't public. So we had to understand the paper and build the lighter version of it on our own. So to conclude, our study implementation shows that multimodal embedding significantly help RL-based driving. The TD3 policy is definitely more stable and more weather aware than imitation learning. And even with data and time limits, the experiment demonstrated how perception and reinforcement learning interact in a realistic autonomous vehicle pipeline. Thank you.